Hello friends, in our earlier discussion we talked about series circuits and how to apply Ohm's law and Kirchhoff's voltage law. You also saw how a series circuit can be used as a voltage divider to obtain several specified voltages from a single source voltage. The effects of opens and shorts in a series circuits were also examined. In today's lecture, we will see how Ohm's law is used in parallel circuits, and we will discuss in detail Kirchhoff's current law. Also several applications of parallel circuits including automotive lighting, residential wiring and internal wiring of analog ammeters will be discussed. You will learn how to determine total parallel resistance and how to troubleshoot for open resistors. When resistors are connected in parallel and a voltage is applied across the parallel circuit, each resistor provides a separate path for current. The total resistance of a parallel circuit is reduced as more resistors are connected in parallel. The voltage across each of the parallel resistors is equal to the voltage applied across the entire parallel circuit. Resistors in parallel. When two or more resistors are individually connected between two separate points, they are in parallel with each other. A parallel circuit provides more than one path for current. Each current path is called a branch, and a parallel circuit is one that has more than one branch. Two resistors connected in parallel are shown in figure A. As shown in part B, the current out of the source divides when it gets to point A. It goes through R1 and I2 goes through R2. If additional resistors are connected in parallel with the first two, more current paths are provided between point A and point B as shown in part C of the figure. All points along the top shown in blue are electrically the same as point A, and all points along the bottom shown in green are electrically the same as point B. A rule for identifying parallel circuits is as follows. If there is more than one current path, that is branch, between two separate points, and if the voltage between those 2 points also appears across each of the branches, then there is a parallel circuit between those 2 points. The figure here shows parallel resistors drawn in different ways between two separate points labeled A and B. Notice that in each case the current has two paths going from A to B, and the voltage across each branch is the same. Although these examples show only two parallel paths, there can be any number of resistors in parallel. Voltage in a parallel circuit. The voltage across any given branch of a parallel circuit is equal to the voltage across each of the other branches in parallel. Each circuit path in a parallel circuit is called a branch. To illustrate voltage in a parallel circuit, let's examine this figure. Points A, B, C and D along the left side of the parallel circuit are electrically the same point because the voltage is the same along this line. You can think of all of these points as being connected by a single wire to the negative terminal of the battery. The points E, F, G and H along the right side of the circuit are all at a voltage equal to the positive terminal of the source. Thus, Voltage across each parallel resistor is the same and each is equal to the source voltage. Note that the parallel circuit in figure resembles a ladder. Now this figure here is the same circuit as in part A, drawn in a slightly different way. Here the left side of each resistor is connected to a single point, which is the negative battery terminal. The right side of each resistor is connected to a single point, which is the positive battery terminal. The resistors are still all in parallel across the source. Kirchhoff's current law. We learnt in previous lecture that Kirchhoff's voltage law deals with voltages in a single closed path. Kirchhoff's current law applies to currents in multiple paths. Kirchhoff's current law, often abbreviated KCL, can be stated as follows. The sum of the currents into a node, that is total current in, is equal to the sum of the currents out of that node, that is total current out. A node is any point or junction in a circuit where two or more components are connected. In a parallel circuit, a node or junction is a point where the parallel branches come together. For example, in the circuit of figure, point A is one node and point B is another. Let's start at the positive terminal of the source and follow the current. The total current IT from the source is into node A. At this point, the current splits up among the three branches as indicated. Each of the three branch currents, that is I1, I2 and I3, is out of the node A. Kirchhoff's current law says that the total current into node A is equal to the total current out of the node A, that is I total is equal to I1 plus I2 plus I3. Now following the currents in figure through the three branches, you see that they come back together at node B. Currents I1, I2 and I3 are into node B and IT is out of node B. Kirchhoff's current law at node B is therefore the same as at node A, that is IT is equal to I1 plus I2 plus I3. This figure here shows a generalized circuit node where a number of branches are connected at a point in circuit. Current I in 1 through I in n are into the node. Currents I out 1 through I out m are out of the node where m can be any number but not necessarily equal to n. By Kirchhoff's current law, the sum of the currents into a node must equal the sum of the currents out of the node. With reference to figure, a general formula for Kirchhoff's current law is I in 1 plus I in 2 plus so on up to I in n is equal to I out 1 plus I out 2 plus so on up to I out m. If all the terms on the right side of the equation are brought over to the left side, their signs change to negative and a 0 is left on the right side as follows, where in1 plus in2 and so on up to plus in minus I out 1 minus I out 2 minus so on up to minus I out m is equal to 0. Based on this equation, Kirchhoff's current law can also be stated in this way, where the algebraic sum of all the currents entering and leaving a node is equal to 0. Now we shall use Kirchhoff's current law to find the current measured by ammeter A3 and A5 in this figure. The total current into node X is 5 milliampere. Two currents out of node X are 1.5 milliampere through resistor R1 and the current through A3. Kirchhoff's current law applied at node X gives 5 milliamperes is equal to 1.5 milliampere plus current through ammeter A3. Solving for current through ammeter 3 yields IA3 is equal to 5 milliampere minus 1.5 milliampere, and it comes out to be 3.5 milliampere. To find the current in ammeter A5, we apply Kirchhoff's current law at node Y. The total current into node Y is IA3 is equal to 3.5 milliampere. Two currents out of node Y are 1 milliampere through resistor R2 and the current through A5 and R3. Kirchhoff's current law applied at node Y gives 3.5 milliampere is equal to 1 milliampere plus the current through ammeter A5. Solving for current through ammeter A5 yields 3.5 milliampere minus 1 milliampere, and current through ammeter A5 comes out to be 2.5 milliampere. Total parallel resistance. The total resistance of the circuit decreases when resistors are connected in parallel. The total resistance of a parallel circuit is always less than the value of the smallest resistor. For example, if a 10 ohm resistor and a 100 ohm resistor are connected in parallel, the total resistance is less than 10 ohm. As we have learnt, when resistors are connected in parallel, the current has more than one path. The number of current paths is equal to the number of parallel branches. As shown in figure A, there is only one current path because it is a series circuit. There is a certain amount of current I1 through R1. If a resistor R2 is connected in parallel with R1 as shown in figure B, there is an additional amount of current I2 through R2. The total current from the source has increased with the addition of the parallel resistor. Assuming that the source voltage is constant, an increase in the total current from the source means that the total resistance has decreased in accordance with Ohm's law. Additional resistors connected in parallel will further reduce the resistance and increase the total current. Formula for total parallel resistance. The circuit in figure shows a general case of n resistors in parallel. N can be any number. From Kirchhoff's current law, the equation for the current is I total is equal to I1 plus I2 plus I3 and so on up to In. Since Vs is the voltage across each of the parallel resistors, by Ohm's law, I1 is equal to Vs divided by R1 and I2 is equal to Vs divided by R2 and so on. By substitution into the equation for current, Vs upon RT comes out as shown here. The term Vs can be factored out of the right side of the equation and gets cancelled with Vs on the left side, leaving only the resistance terms as an equation where 1 upon RT comes out to be 1 upon R1 plus 1 upon R2 plus 1 upon R3 and so on up to 1 upon Rn. Recall now that the reciprocal of resistance is called conductance, which is symbolized by G. The equation for 1 upon RT can be expressed in terms of conductance as Gt is equal to G1 plus G2 plus G3 and so on up to Gn. Now we solve for RT by taking the reciprocal of both sides of the equation for 1 upon RT as shown here. So RT comes out to be 1 upon R1 plus 1 upon R2 plus 1 upon R3 and so on up to 1 upon Rn. This equation shows that to find the total parallel resistance, add all the 1 upon R or conductance terms and then take the reciprocal of the sum. So RT comes out to be 1 upon Gt. The case of two resistors in parallel. The equation we deduced in the earlier section by finding the reciprocal is a general formula for finding the total resistance for any number of resistors in parallel. The combination of two resistors in parallel occurs commonly in practice. Also, any number of resistors in parallel can be broken down into pairs as an alternate way to find the RT. Based on equation, the formula for the total resistance of two resistors in parallel is given by this equation where RT is equal to 1 upon R1 plus 1 upon R2. Combining the terms in the denominator yields RT is equal to 1 upon R1 plus R2 divided by R1 into R2, and this can be rewritten as RT is equal to R1 into R2 over R1 plus R2. Now this equation states that the total resistance for two resistors in parallel is equal to the product of the two resistors divided by the sum of the two resistors. This equation is sometimes referred to as the product over the sum formula. Parallel circuit applications, automotive. One advantage of a parallel circuit over a series circuit is that when one branch opens, the other branches are not affected. For example, figure here shows a simplified diagram of an automotive lighting system. When one headlight on a car goes out, it does not cause the other lights to go out because they are all in parallel. Notice that the brake lights are switched on independently of the headlights and tail lights. They come on only when the driver closes the brake light switch by depressing the brake pedal. When the lights switch is closed, both headlights and both tail lights are on. When the headlights are on, the parking lights are off and vice versa. If any of the lights burns out, that is opens, there is still current in each of the other lights. The backup lights are switched on when the reverse gear is engaged. Another common use of parallel circuits is in residential electrical systems. All the lights and appliances in a home are wired in parallel. Figure shows a typical room wiring arrangement with 2 switch controlled lights and 3 wall outlets in parallel. So friends, this brings us to the end of our discussion in this lecture and therefore we sum up. In this lecture, we learnt that when two or more resistors are individually connected between two separate points, they are in parallel with each other. If there is more than one current path between two separate points, and if the voltage between those 2 points also appears across each of the branches, then there is a parallel circuit between those 2 points. The voltage across any given branch of a parallel circuit is equal to the voltage across each of the other branches in parallel. Kirchhoff's current law can be stated as the sum of currents into a node, that is, the total current in is equal to the sum of the currents out of the node, that is, total current out. So that is it for today. In the next lecture, we shall be discussing about voltage dividers, measurements and power in series circuit. Thank you very much.